Is it good now? Okay. So, should I start from the beginning again? Okay. Olivier, you come back? Come back. Come back. Okay.
So we lost William.
We lost William. Okay.
William's height.
William Brown.
I get a second shot because this is great.
Yes.
I'm William Brown. I'm a biophysicist with the International Space Federation. I've been working with Nassim for over 10 years now. And what we have been doing is looking at or investigating the physics operational in the biological system. So by looking at the remarkable solutions that are coming through with the unified physics, so that's like finding the similarities, the coupling between gravitational space-time and the quantum vacuum and the electromagnetic field, we can see how that is operational in the biological system to better understand life and the living system. So as an example, we're looking at how energy flow through the cell, energy flow through the cellular system structures information. And as we all know, information is at the root of life. And we can already begin to see parallels between the latest work, the origin of mass and the nature of gravity, and the biological system's organization. So in the origin of mass and nature of gravity, we see the essential role of energy and information flux across gradients, producing or generating, resulting in mass, resulting in force, the confinement forces. It's possible, one of the things we're investigating is that could be scaled up into macro scale systems. And what you will have is the conditions for the emergence of the living system via those kind of gradients that have that energy and information flux.
Yeah, like energy, like a flow or a pressure moving across a semi-permeable membrane, like splitting electrons and protons, right? Like in the mitochondria producing the energy for the cells. We just looked at some numbers lately and it was just amazing. I was flabbergasted that the numbers that come out, like what was it like for the biological structure, like the amount of charge that it gathers?
Yeah, that's one of the things is, we're talking about biological system and you're thinking, well, that's low energy system.
Low energy system, yeah, exactly.
Especially compared to the proton.
Right.
That's a high energy system.
Or a black hole.
Black hole.
Yeah.
But actually, if you look at the latest measurements on the electrical field stream within the mitochondria, so you've got the semi-permeable membrane that's segregating protons and electrons. Mm-hmm. The electrical gradient that's building up across that, it's about 180 millivolts, but that's across a 2 nanometer thick membrane.
Right.
So if you were to actually scale that up to a meter, it would be like 30 million volts per meter.
Right.
So it's actually an extremely large energy density.
Yeah, because there's a lot of mitochondria, right?
And so you've got 1 billion mitochondria in the average human body.
Or in my body, so.
Which is the equivalent of about 4 football fields of surface.
Yes. So it's not a meter square, right? It's 4 football fields of serious energy density.
4 football fields and 30 million volts per square meter. I mean, that is a lot of.
That's a lot of juice.
Energy.
Yeah, that's. I mean, that's lightning is close to a meter square of that energy, right?
It's equivalent to a volt of lightning. Now,
Yeah.
a volt of lightning is 15 to 30 million volts per meter.
Right.
That's the charge across
The boundary.
across the mitochondrial boundary.
Yeah, amazing.
Of course, but it's you're talking about a nanometer section of that 30 million volts per meter, so
Right.
it's 180 millivolts in a little nanometers section.
Right.
But then the flux rate of protons through the system, it's on around the value of 10 to the power of 21 protons per second,
Per second are moving across that boundary.
moving across this semi-permeable membrane.
Insane. You know, it's high energy physics. And, you know, it's really not thought that way because we have a tendency to cut the things in pieces and not look at the whole dynamic.
And when you start to add the values all together, it's astronomical.
It's remarkable.
It's actually
But literally astronomical.
literally
Yes.
because 10 to the 21, that's the values you get for like the number of stars in a galactic cluster. It's just a few orders of magnitude lower than the total number of stars in the observable universe.
In the observable universe. Yeah, it's remarkable. Anyway, we were having fun. Cyprien, what are you doing here?
Hello everyone, good evening. I'm Cyprien Guermont-Prey and I'm a physicist. I did my PhD in fluid mechanics and I joined ISF like over a year ago, and I'm working with Olivier and Nassim on the holographic mass solution, and you probably read my name on the paper we just published last year, and we are working on the next two papers, and I'm bringing this specificity of fluid dynamics, especially for the second paper where we'll describe more deeply the Planck plasma flow and how the mass emerged from this flow and about the dynamics of the Planck plasma flow. And I'm really happy to be here tonight with you guys.
It's really good to have you.
Yeah.
Thanks for being here.
Hi everyone, I'm Olivier Lirol, and I have a PhD in nuclear physics, and I'm working with Nassim since 2017, and it's been quite a journey. And I'm working with him on both the theoretical side and the applications that are directly connected to the equation we are currently writing with Nassim and Cyprien. And it's going on, both the paper and the application. So, and you can see the lab.
Yeah.
It's clean.
Well, welcome to our lab.
It was cleaned for the equation.
And no, it's always clean. What are you saying? You've been involved as well in like working on the equations that we eventually have ready to move into the second paper. So, Olivier has been working with us for like how many years? 6 years, 7 years?
Yeah.
And so, Olivier and I actually elaborated a pretty straightforward, path. And we found that there was just so much information, and there's still just so much that we had to cut it in pieces. So this first paper is really just the first piece, and that's why, some of the more technical people might say, oh yeah, but you didn't do that. That's coming, right? It's just coming in the next paper. So, with Cyprien and Ines and William, we're cleaning up the other papers, and with William, we're working on the biophysics paper, which I'm super excited about because we found amazing things for that as well, because there's so much data that's coming out, mostly about the brain these days. We just published a little articles about it, and
Also in astrophysics.
and in astrophysics, and the links are just coming, it's plugging in super nicely, so I'm excited about that. Okay.
Hi, so I'm very happy to be here. My first visit to labs here in France. I'm Ines Urdaneta. I'm from Venezuela originally, but I currently most of the time working from Mexico. So I'm a physicist. I did my PhD in nanotechnology at the University of Paris-Ons here in France. Nanotechnology basically in molecular wires, in theoretical developments of molecular wires coupled to time-dependent electric fields. At this moment, I'm part of Nassim's research team since 2018. And so very excited to be collaborating in these projects with him, also focusing particularly in an aspect of the electron, which is called the Sitter-Bewegung, which has been like my obsession.
We'll just call it the zitter.
Sitter-Bewegung.
Yeah,
Sitter.
the cedar, because like otherwise I can't do it. It's too hard.
Yeah, it's an aspect that is predicted by Dirac's equation. And it's very interesting to meet. Having done that research, it's interesting to have it to meet people on the physics domain that are very interested in this aspect of the electron, which is described as a real physical rotation, not as it is usually described as a difference, like a cloud of probability distribution in space. In this case, the way we are developing it, it's a real rotation in the field, in the quantum vacuum field. So it's just falling in perfectly well with everything that's being done here as well.
Yeah, and you're not the only one thinking about it this way. There's a bunch of scientists around the world, right?
Exactly.
Some with pretty high reputations.
Yes, the community is very large and they're kind of
Growing.
yes, they're growing.
Yeah,
Yes.
because the interpretation that's currently there is so unphysical that a lot of physicists are starting to like say, wait, maybe there's a more elegant and physical way to look at this.
Totally, yeah.
Yeah,
Yeah.
wonderful. All right, so we were gonna start with a presentation. Cyprien, if you want, you can go at it, and there we go. Let's see, we have a screen in front of us, so if I'm not looking at you guys directly, it's because I'm looking at the screen a little bit. So we wanted to present lightly in a layman way the paper we written, because people are asking a lot of questions. Well, in general, people are wanting to understand what exactly we wrote, right? So if you would like, we would like to present it to you in a more, we're gonna kind of fly through it. You're gonna see equations fly by. If you're a technical person, it's in the paper, so you can go and look in the paper, but if you're not a technical person, just we'll just explain the fundamental principle that the equations are describing, because it's actually pretty straightforward. So let's start with the presentation. So why did we write a paper called The Original Mass? Oh, we switched already. Why? You're killing me. Come on. I can't talk that fast. So we called it The Original Mass and the Nature of Gravity because that's what's in the paper. But why are we addressing that? Especially layman's might think, of course, we know what mass is. Of course, we know what gravity is. And the first few slides we're going to show you is just to show you that actually that's not completely true. Like there is a lot of questions about mass and gravity, and in general, if a physicist is honest, they will tell you that mass, the origin of mass is an unknown, and gravity is known to a certain extent, as is Einstein told us that it's the curvature of space-time, but didn't really tell us what space-time is made of. What is that thing that we call space-time? And fundamentally, even, more formally, we actually can measure gravity. We can, predict path of objects in the universe. we can do a lot with Einstein field equation, but we can't, in general, the physics community cannot tell you exactly where gravity, what is the origin of gravity. So in this paper, we resolve these things, and they're not small things. They're really foundation things, fundamental physics. And so, for instance, we start with the most common equation. And you know, if you come to one of my talks, I'll be more elaborate about that, but now you can switch. Okay. Cyprien, you want to describe a little bit the Einstein triangle?
Yeah.
So that's special relativity.
So yeah, it's special relativity, and the concept with which Einstein came with was that the elementary element in physics is not the mass anymore, but it's the energy. And he wrote this equation from special relativity, where we can see that there is what we call the rest mass of the particle that gives the potential energy, and there is also the momentum energy. And what we call momentum is when the particle is moving through space, when it has a velocity, it gives it a momentum.
Like a kinetic.
Yeah, like a kinetic energy. So if we put the potential energy on one side of the triangle and the kinetic energy on the other side, by applying Pythagoras, we can deduce the total energy
of the system, which is E sub P plus E sub K, right? So the potential plus the kinetic.
Exactly, yeah.
Is the total energy. I think it's really cute that it's on a Pythagorean triangle, right? Because people may not realize that, like this geometry can be used to extrapolate something much more profound about the nature of reality.
Exactly, and I think it underlies the fact that even special relativity has its roots in geometry.
Yeah, it gives a hint that there's an underlying geometric relationship, because the hypotenuse is the value of the energy of the system. So if you're trying to measure so the result is that if a particle is said to be at rest, that is, it's not moving relative to you, and we could get into that discussion, but okay, then the PC square is zero, right? It is no momentum, and so the result is E equals mc square, which is the common equation,
the famous Einstein
equation for the energy of a system, right? For energy of a system at rest. However, and we all use it. It's used everywhere. Everybody knows it. It's probably the first equation you learn in school, right? In primary school, right?
Yeah, it's more like folklore and.
Folklore.
Yeah, because you are not really using it. You are using it when you do nuclear power, this kind of stuff.
Right.
But it's not middle school or high school that you are using it.
Yeah. But everybody, it's a beautiful equation. It's used in many other things in physics, and it's commonly used in physics everywhere. However, to transfer mass into energy. So it tells us something profound, that there's a relationship between an equivalence between mass and energy. So it's very important because it gives you a hint on the nature of mass right there. Except, that if you look at the equation in terms of fundamental physics, we don't know, right? If you click, it's going to say undefined, right? Mass is undefined. It's a concept we have. And, for the layman's, it's easy to confuse mass with weight. Weight is not mass. Weight is the mass energy in relationship to a gravitational field. So like you weigh that much here. If I bring you on the moon, you'll weigh 1/7 of that. Depending on the gravitational field that you're around, your weight will change, but your mass will always remain the same. That's the energy of the system. But we use this word mass, and Einstein showed us that we mainly mean energy, but do we even know what energy is? Because C is undefined as well. So meaning that we know the speed of light, we can measure it, and we could have a debate about that because we only measure the speed of light, as it bounces off a mirror, and we assume it's going at the same speed going there than coming back. There could be a debate about that, but let's say we measure the speed of light, we'll assume that. It's pretty fair assumption. However, we don't know why the speed of light is the speed of light. Why is it that speed? Why isn't it a kilometer faster a second or a kilometer slower a second? We don't know why the speed of light is the speed of light. And so we have two unknowns on the right side of the equation, so that makes an unknown on the left. So we don't really know what energy is. We use it every day. We actually convert energy to electricity. We make, a magnetic field, electromagnetic field. We use all this all the time. And we know it can produce work. We can make it work for us, but we don't actually know fundamentally where it comes from in the universe. So this is why we wrote this paper.
Yes, exactly. Yeah.
Okay.
And another observation is also, shouldn't be the proton mass, the origin of the proton mass already known by the Higgs mechanism? And one thing that, you have to keep in mind is that the Higgs mechanism only predicts up to 5% of the proton mass.
Okay, they might not know what the Higgs mechanism is. You remember a few, 7 years, 8 years, 10 years ago?
10 years ago.
Yeah. You signed the papers everywhere. The God particle was discovered, right? At the LHC and, at the accelerator in Switzerland, and that they had found this Higgs boson, which is supposed to be the source of mass and all this. Well, actually, when you do all the rest of the theory and you follow the standard model, you find that actually the Higgs boson only predicts 5% of the mass of the proton, and the proton is the mass of the universe, meaning when we calculate the mass of the universe, we generally ignore the electron because it's so little compared to the proton. Most of the mass of the atoms is in the nuclei, which is so much smaller than the atom, and it's all concentrated in the proton there, and so that's why the proton is really important if you're trying to find the source of mass.
Well, and the neutron immediately decays into a proton outside of the nucleus.
Outside of
So people are saying, well, what about the neutron? It's
a proton in disguise. So if you consider that, then the Higgs mechanism, the so-called God particle, which is to me is a little bit of a horrifying terminology, is only able to predict 5% of the mass of the proton. And then we'll see that actually is diminished when you apply it to the universe for other reason, and we'll see that later. But so it's certainly not a complete view of where mass come from. In our equations, we get 100% of the mass of the universe and the mass of the proton. So in our case, there's not this issue, and we're gonna go through that. Okay, let's keep going because otherwise we'll take the 2 hours just on the presentation, right? And so basically, you can see on the left there is like Einstein special relativity. On the right is general relativity, and you know, why did Einstein generalize special relativity? Because what's missing in E equals mc squared is G. You know, it's missing gravity. Like, clearly gravity is related to mass somehow. I was clear to Einstein that like mass created gravity, like wherever there's a massive object, you know, gravity's around. And so that was, you know, part of the evolution of his work and his equations.
Yeah,
So-
because from Newton mechanics, I mean, the first of the equation that were produced by Newton was that when we have two mass, there is a gravitational force. So Einstein thought that there might be a connection between like defining the mass and also the gravity. So
Yeah, so
he attempted
to find a solution.
find a solution
Because
to gravity.
because Newtonian idea was that the mass was some kind of inherent behavior of mass.
Yes.
And Einstein said, no, it's a behavior of the space around the mass, which eventually became space-time. And you know, I want to make another point clear, is that when Einstein wrote those equations, first of all, he was using the mathematical tools of the time. It could have been written in a whole lot simpler way, right?
Yeah, exactly.
It could have been written in what is called today geometric algebra, Clifford algebra, and so on. And it would have been analytical, which Einstein tensors equations are not. And it would have, I think, been much more complete. You know, the way he wrote it was good enough, first approximation, to confirm the effects, the curvature of space around the mass, right?
Yes, exactly, because they could predict the deviation of light due to massive objects in space, and also
So a star that was behind the sun appeared like it was beside the sun because the light of the star was being curved by space around the sun,
exactly.
right?
Yeah, right.
Yeah. And then it had an influence as well on the orbit of Mercury.
Yes.
That was confirmed, and so on. So then, you know, those equations became the standard over time to describe the gravitational field.
Exactly.
So let's look at these equations a little bit. So if we look at the equation below there, below the image,
Yeah.
do you want to point at it? Yeah. Okay. So on the left side of the equal sign is the metric, right? That is like the elasticity of space-time curving, the space curving around the object, around the mass. And then on the right side is what is called the stress energy tensor. It's the part that is describing the mass, the energy of the mass, curving space-time. And so typically, physicists will tell you mass tell space-time how to curve, and space-time tells mass how to move, meaning like it's going to define the way an object spins around the system.
Yeah, like a moon around the planet.
Like a moon around a planet. Yeah, exactly. But when Einstein wrote this, actually the complexity was so high, and he didn't have like computing powers like today and so on. And so he couldn't solve it. He just wrote the equations in such a way that like it would make sense, but there was no somewhat exact solution to the whole riddle. And luckily there was a physicist, mathematician on the front in Russia from Germany that saw Einstein's paper, and his name was Karl Schwarzschild, and he thought, hey, he actually was sick at the time that he read the paper, and he was actually on his deathbed, and he actually solved the first solution to Einstein's equation, that's called a Schwarzschild solution, and so it's called Schwarzschild. And he sent it back to Einstein. The only thing is that the solution to Einstein's equation is a black hole. It's not anything else, meaning like it always involves a black hole being present at the center of the equation, meaning you can't get rid of the black hole. And so Einstein was actually, I believe, from what I read in history, a little discouraged because he thought, oh, maybe my equation is wrong. He didn't believe there could be a mass in space that would be so strong that light would be sucked in. And so it was like a little confusing. And yeah.
And the issue was about the two singularities at the time that were appearing.
Right.
One at the center and one at the horizon.
And one at the horizon. And eventually the one at the horizon was shown to just be a choice of coordinates. You could change
Mathematical artifact.
a mathematical artifact, but the one in the middle definitely was real. You just couldn't get rid of the black hole. And so at the time that was thought to be a black hole was thought to be something that could not exist. So in general, they just ignored that part because it was giving the right the right answers.
Yeah, it could match the observation.
It could match the observation in the weak field, far from the black hole. But every time we use Einstein, every time we use general relativity, we're making black holes, right? Like in the equations, if we're looking at the movement of a planet around the sun, we actually make the sun a black hole and the planet a black hole in the equations, and then we get the right path, we get the right answers. But we do make them black holes, and I want to make that clear. Then the other thing is that we assume the mass, meaning Einstein just said, okay, we're plotting a mass on a surface, like I'm putting a heavy ball on a trampoline and it's curving the trampoline. The mass is not, described physically, like where it comes from, how to get there. It assumes that this place is where there's no mass, for instance, which is not anywhere we found in the universe, and all this stuff. So basically, it's somewhat artificial, and what Cyprien just made appear on the slide is that there is nowhere in the literature where actually space-time, the metrical side of the equation on the left, actually comes back and make the mass. And that is the part that we believe is missing, is that actually space-time is a fluid, actually, the equations are fluid dynamic equations, but it is a fluid dynamic, like a real fluid structure, like a plasma structure, like electromagnetic plasma. Plasma is like the medium on the sun is a plasma. We see a lot of
Fire.
Fire is a plasma, exactly, and it's plasma at a higher scale than what we're talking about. We're talking about a plasma, a fluid dynamic that's occurring at a scale that's billions and trillions of times smaller than the atom, so we don't experience it directly. But its dynamics is what produces mass, and we're going to see that, and gravity.
And a good illustration of this issue of this decorrelation in the current theory between mass and gravity is the fact that they found the mass with the Higgs mechanism, but they didn't find quantum gravity at the same time.
Right.
Showing that the mass that they found wasn't linked in any way, shape, or form to gravity.
To gravity. So clearly, then it's incomplete. It's not complete. Let's keep going, otherwise we're never going to finish. Okay, so So I wanted to show you as well that so there's another problem with mass is that when you take general relativity, Einstein field equation, you apply them to the universe, you're missing some 96% or 95% of the mass of the universe. So people ask me, but what do you mean by that? What I mean is that when we look at the universe, we can tell how much mass the universe has to have in order for things to orbit the way they do, either inside a galaxy or, galaxies and superclusters and all this in the universe and how the universe is expanding. And when we use Einstein's equation, we end up deficient with 95% of the mass missing for it to behave the way we see it behave. So it's non-trivial, and so Einstein field equation in some ways only predicts 4.9% the mass that we see, which is baryonic mass, so that would be the protons in the universe. But the rest is something that we fudge. The standard model had to come up with something, so they invented dark energy and dark matter, assuming that they were going to find it at one point. Dark matter to put inside galaxies so stars don't go flying and the gravity is strong enough, and dark energy so that the universe is expanding and accelerating as we see it do. And so the result is that when we combine those two, the Higgs mechanism that only predicts 5% of the mass of the proton, and the general relativity that only predicts 4.9% of the mass of the universe, we end up with our theories as a whole, quantum gravity, quantum physics, and general relativity, only predicting 0.2% of what we observe, right?
But they say it's rigorously calculated.
Yes, it's rigorously.
It's only 2% or much less, but it's really well calculated.
It's well calculated, exactly. And I don't know if when I passed exams when I was in school, coming up with an answer that's 0.2% of the right answer would have got me a good mark, but I don't know. But basically, 99.7% of the universe is basically unknown to the standard model of physics. It's an unknown mass energy that's occurring, and that's a big deficiency. And you might think, oh, well, we'll just go out there and look for dark matter and dark energy and it's going to solve everything. Well, they've been looking for dark matter and dark energy, dark matter particle for at least 2 decades, I think, at least. And they can't find it, of course, because most likely it doesn't exist. Because when you solve the equations with the vacuum fluctuation, with the structure of space, with this Planck plasma that permeates everything, which is a natural occurrence of the equations of quantum mechanics, then you don't have this issue. So let's get into it. So the beginning of quantum mechanics started with Max Planck. Is generally given the title of the father of quantum mechanics. And how did that start?
Actually, Max Planck was asked to optimize the filament in light bulb, and so he tried to understand a little bit better how the color of the light was related to the temperature of the filament. And at the time, at the end of the 19th century, they had a lot of measurements comparing the light emitted by different objects held at different temperatures, and this is what we call black body experiments, meaning that a function of the temperature of a black body what would be the light that the black body would absorb and what would be the light that would be emitted by the black body.
Yeah, you gotta tell them what a black body is. What's the description of a black body? It would be an ideal body, right?
Yeah, an ideal body that will absorb
All the light that's incident on it. What does that make you think of?
I think it's start with a black or so, black hole.
Black hole? Oh, yeah.
But the funny thing is that the black body is not black.
Right.
Because of course your bulb is not
It's not black.
bright.
It's bright. Right.
Because it's at a certain temperature.
Right.
So
Exactly.
the black body term is more like a physical term for physicists.
Yeah.
But it doesn't describe really like the
A physical thing.
Yeah.
Yeah. It's a concept.
Yeah, it's a concept. That you can represent experimentally with a black box,
Right.
with black paint.
With black paint. You can make one.
Yeah.
Yeah,
But
that
it's very-
absorbs. Yeah.
Still conceptual.
And yes, but you'll get the right answer in laboratory if you do it. It's just that at the time, the classical theory to give the wrong answer. And that's what Planck was trying to solve, right? It said that the black box should emit infinite amount of ultraviolet
Yeah,
Yeah.
UV light.
UV light.
The ultraviolet cultures. But to be clear for everyone, every object can be modeled as a black body.
Right.
Like your body is a black body,
Yeah.
the apple on the table is a black body.
Yeah, because
The sun is
everything,
a black body.
yeah, the sun is almost a perfect black
Is
body.
almost a perfect.
Yeah, because a perfect emitter would be a perfect absorber.
Exactly.
Yeah. So that actually, but you have to understand, although Max Planck wrote this equation before general relativity, when general relativity occurred, and the black hole thing came out, everybody thought black holes didn't exist. It was not till the 90s that actually black holes got confirmed
And the
observationally.
term was coined by Wheeler in the 60s.
Yeah, exactly. Well, students of Wheeler, and Wheeler popularized it, and so the idea that the black box or the basis of quantum physics may be related to black hole is still not around.
Yeah.
Although actually quite a bit of people actually tried to use that and throughout the
And
ages
they are using it with the Hawking radiation,
with Hawking radiation and so on,
but
but
only partially.
only partially.
Very partially.
Yeah, so it's not being completely integrated together because these things were discovered at such large, distances from each other in time, and so the theories went in other directions. So the idea of a black body radiator at the quantum level being related to a black hole, which is cosmologically described,
A gravitational object.
a gravitational object, has not been put together. And the piece that's missing between the two is quantum vacuum fluctuations. So let's keep going though, because that's what Max Planck discovered. So he found he had to add a constant in the classical equation for the equation to give the right answer, right?
Yeah, and what we mean by the right answer is to find the experimental observation that was made like 50 years before him by Kirchhoff, relating the temperature of a body and the light that was emitted by this body.
The
And
emission spectrum.
The emission spectrum.
The emission spectrum.
Yeah.
And
And so by adding this constant, you want to point where is the
yeah,
constant in the
so it's H bar here.
H bar.
And
Initially H, it became H bar with Dirac,
Yes.
right? And
Yeah, he quantized the electromagnetic field.
he quantized the electromagnetic field. So basically, he didn't like that answer, by the way. He wrote extensively that, he didn't think that was right. It's just the only thing he could come up with to make the equation work. He felt like it was a fudge factor. It didn't seem instinctive that the electromagnetic radiation of an object would come out in little packets because it basically, that's where quantum theory came from. It basically said it was coming out in quantas,
Yeah.
which eventually Einstein called photons,
Yeah, with the photoelectric effect.
with the photoelectric effect, which he got the Nobel Prize for. So people think Einstein got the Nobel Prize for general relativity. He didn't. He got it for actually contribution to quantum mechanics. Yeah. And so, so basically that's really important to understand. Basically, and you see the application of Planck's law on the light bulb box you buy. On the light bulb box, it will tell you at what Kelvin, the bulb is rated. Like on the one we have on there, you want to point it out? I think it's rated at 3,000
Yeah, it's
on the box. No, on the box here, yeah.
3,000.
3,000 Kelvin.
Yeah.
So this is this is actually a direct consequence of these equations, which are at the basis of quantum mechanics.
So to be clear, this value were the exact temperature value when it was an incandescent bulb. Now it's LEDs, so it's an equivalent.
Right.
LEDs are not black bodies.
Yeah, yeah.
So it's more photoelectric effect.
Yeah, it's
a-
photoelectric. Yeah. Okay.
so way more efficient.
Yeah. So here we're just showing that the sun's a black body. I think that slide is a little bit out of sync. Okay, so H, which eventually became H bar, because in later computation, Dirac showed that it actually is H over 2 pi. And the reason I'm showing you that, because you might remember from high school, 2 pi would represent like a circumference,
Yeah.
right? And so H is it's an energy over a circumference, so it's a movement, an action, right? And that action is basically a angular momentum. So H bar is like a little spinner, right? It's like a little angular momentum. And so the result is that you can have another equation that's not as well known to describe E, right? To describe energy, that says E equals H bar. So if we had put H, it would be H over 2 pi multiplied by the pulsation, the amount of time it's going around, right? And that would be the energy of the little oscillator. And here we're showing that one is from quantum mechanics, the other one is from relativity, but the equivalence between the two, like it's never been mushed together and put together in like a proper, clear way. They both give energy.
They tried.
They tried, yeah, but
It's the Braille.
yeah, but it failed. And it failed because it's missing a field that relates quantum mechanics and relativity.
And it also gave the first conclusion, which is kind of not correct, about the wave-particle duality. Because
Right.
when De Broglie had this unification of these equations, they suddenly found, there's then this equivalence between wave and particles.
Yes.
Which then got diverted through the Copenhagen interpretation in
Right.
mechanics.
With the double slit
with the
experiment.
double experiment. So this has much further.
So now things becomes really esoteric in physics, what Ines was saying, and things can be particles and waves at the same time, and now your brain is dislocating, and now forget physics. At that point, you're only doing mathematics because you're doing probability functions and so on, and you're not actually having a visual. And literally, physicists tell their students, don't try to visualize it, shut up and calculate. That was Feynman. Basically, don't try to think of it as some physical thing. It's totally esoteric. And that's where we believe that, I'm going to talk to myself, that's where I believe that physics went astray, and it became mathematical physics, and it became completely divorced. And we'll show another example where it divorced from reality, because if you consider pilot wave theory, which actually says that when you're shooting the particle at the two slits, it's moving in a field. Well, then, of course, just like a boat on the ocean, when the particle moves, it makes waves. So it's not a particle in a wave in an esoteric way. It's a particle in a wave, because when you move anything in the field, you're making waves. In fact, even when it's at rest, it's making waves, and these waves actually happens to be its mass. And that's what we demonstrate.
And they are measuring it even with the gravitational field, with what they call frame dragging.
Right.
The fact that the field is changed by the motion of the
particle. Yeah, exactly. So, there's a lot there, and like we could talk forever, and I want you guys to be able to ask questions. So, yeah, let's keep
and
going.
we have some good questions.
Oh yeah, we have some good questions. So let's do it.
This was
So,
just reminder that when Max Planck created his new theory of black body radiation, he had to use this model of an harmonic oscillator.
Yeah, he had to start with something.
Yes, exactly.
So he imagined the atom as like the atom that made the filament of the light bulb as a bunch of like resonating cavities or oscillating cavities.
Yeah.
And he wrote the math for it. The thing is that students in school get visualized, instead of a cavity like a sphere that's spinning, right, which would be more consistent with H bar, they get told that the oscillator that they're describing in the math of quantum mechanics is a ball, or like a weight on the end of a spring oscillating up and down, which is definitely not what the universe is doing. And of course, it's mathematically equivalent to a sphere spinning, but it's not, it's giving the students the wrong image of what they're actually writing math on. And that's really a problem, because again, you get divorced from the reality of what you're describing. And so it's very hard to find, the truth about it if you have the wrong model in your head. So in the paper, we right away establish that we're not talking about a spring. We're talking about an oscillator that's spinning. And, these little animations show you that there's a direct equivalence between the two. And so that's the equation for the thermal, internal energy of the system, derived from Planck's law, derived from his mathematics. And when he wrote these equations, something weird happened. Like a term appeared, 1/2 of H bar omega, and that was like weird, because it was like saying something really, really strange. So remember, the equation is telling you at each temperature how much radiation there's gonna be, right? Mm-hmm. Well, this part, the 1/2 H bar omega, basically says that even at 0 Kelvin, okay, so at 0 Kelvin, there should be no radiation, right? The thing should be frozen stiff, right? Zero, absolute zero is damn cold. Just call it that way, right? It's not supposed to be moving. But the equation said it gives all the right answer for the rest of the stuff, so you can't just discard it. It says that even at 0 Kelvin, there's an infinite amount of energy. Like that the oscillator has an infinite amount of energy.
Yeah, because here we have to sum on all the omega that are available in the universe. And
so basically it's saying that you have to add up all the frequency of all the fields in the universe,
all the cavities
in the universe, for the equation to be mathematically consistent. And the result is that part of the equation says that at 0 Kelvin, there's an infinite amount of energy. Meaning, at 0 Kelvin, there's still infinite amount of cavities in the universe oscillating, and they're present. It's just not at the scale where you experience it. So let's, of course, the tendency was to remove that term from the equation. But here we give you like a kind of like layman, representation is that you see h bar omega, that part.
Yeah.
Yeah, that part there. That is where a photon is emitted, right? Like now it's radiating heat, it's radiating electromagnetic field. Anything below that, which is the 1/2 h bar omega, everything below that is not available to us. It's not present to us because it's in scales that are not, it's not accessible. It's not at frequencies that we can, it's far, far from what we can measure. So we don't see photons coming out. And so we assume, and so the general consensus in physics since then, so first of all, this is why Max Planck called it 0-point energy. So at 0 Kelvin, it still has energy. And, since then, it's generally being ignored because they basically said, we're just going to start at h bar omega and ignore the rest. Ignore an infinity, which Dirac has some serious issues with it. What was Dirac's quote again? I'm happy to ignore infinitely small values, but I can't really justify ignoring infinite amount of energy, right? Something like that.
But the funny part is that they don't have the mechanism to resolve this infinity, so they want to remove it in an artificial way.
Right.
But every time they need to explain something observed experimentally, they need to put the 0-point energy back.
Yeah,
To
exactly.
explain the phenomenon that they are measuring.
Right. When they find a new particle and so on, they typically start a new field of energy, right?
Yeah, this part too. But with the photoelectric effect, they need like the 0-point energy to explain where the photon comes from.
Right.
Where the electron comes from when it disappears from one orbital and appear on another orbital.
Another orbital.
With the Schwinger effect is when you have a very strong electric and magnetic field. A photon comes out the vacuum.
Out of the vacuum
And they need like
spontaneously.
0-point energy to explain why it's happening.
Yeah,
So
and
they are
the
using-
jiggle of the electron, the lambda shift,
The lamp shift, yeah.
the lamp shift, yeah.
Yeah.
And so, that those are all experimental things that we see in which they have to put 0-point energy back in the equation to make it work.
And even with atoms, when they cool atoms like near 0 Kelvin, they measure still residual energy.
Right, right.
Superfluid helium, that superfluid state is only possible because of 0-point energy. That 1/2 h bar.
That's right. So, it's there, and then eventually there's Casimir that confirms it, but we'll see that later. And so, we've been going, we lost some time at the beginning. I think I'm gonna have to excuse us, for this, but I think we're gonna have to kind of do the presentation in chunks, so we'll pick up where we end at next question and answer time. But we'll try to just get through the correlation functions,
Okay, yeah.
and then we'll stop there.
So that we can answer a few questions.
Yeah, exactly. So we can answer questions.
Okay.
Yeah. So, the slide just before that was Einstein and Wheeler talking about how you can't that objects are actually emerging from the vacuum. The reason they're making these statements is that this 0-point energy just can't go away. It's and the people at that level understood that, the people that are teaching physics today don't necessarily understand that. They think you can just get rid of 0 point just by saying with your hands, oh, well, you know, there's infinite amount of waveforms, so, you know, they all cancel out and you can ignore. So, you know, and that's just not true. It's just completely inconsistent. And it's okay if you're just teaching a certain level of physics, but really actually it shouldn't be taught that way. Because did you get taught about it when you went to school?
Yeah,
You got taught about it
yeah, the standard way.
in the standard way. So what did they tell you? You don't remember? No, that's okay. That's the problem right there. You know?
Basically, the most important problem in teaching physics is we don't have the context. We don't have the question, what were they thinking about, what was the fundamental questions they were trying to answer.
Uh-huh.
So without the historical context, it's difficult to understand why they picked that, what they ignored that, what were the approximation, the standard approximation.
Yeah. Yeah. And you're just trying to like get good notes on your exam, so you're just following what they're telling you. And
and this part you just need to be able to solve the standard question or the standard exercise.
yeah, exactly. Yeah.
You are not like
So it's normal. It's just it should be taught differently. You know, and so continue. So basically, they removed this part.
Yeah, so if we ignore the 0 point energy, if we remove this part,
What does it mean?
Yeah,
what does it do?
what does it do? And by removing this, we remove the source term in quantum mechanics, because all the objects are spinning, all the objects are moving all the time without decaying over the whole age of the universe.
Right.
There must be some source of energy that maintains these rotations, that maintains all the movement in the universe.
Right, but not only that, I mean, it's like if you remove it, then it becomes completely inconsistent. Mathematically and conceptually in the physics. Like conceptually, for instance, you know, an electron would just stop oscillating because it doesn't have a source anymore, right? So it's not just oscillating magically, and it's gonna spiral and fall onto the nuclei, and the atom would have never come to be, right?
Yes, exactly.
So, you know, again, this is another place where physics went awry and it became conceptual. So it's like, oh, we're talking about an oscillator. We're just going to assume it keeps oscillating.
Yeah.
We don't need to show where the hell is coming the energy to make this thing oscillate, right? We're just going to say it all started in the Big Bang. And it's been oscillating since then. No friction, no nothing. When I'm doing that, I'm not affecting the oscillation of my oscillator.
they use perpetual motion.
Right. They use perpetual motion everywhere. And then when over Unity inventors try to tell them that there might be a way to get like something that like is
It's similar.
then they tell you that you're insane and that you don't know physics because it's not possible. But they do it. I mean, the Big Bang is the most magical break of energy conservation. Like you basically just invented all the energy of the universe, and you just start from there, and you don't say where it came from.
And you break the speed of light limit.
And you break the speed of light limit, you know, with inflation by billions of times faster. The universe inflated billions of times faster than the speed of light, which is like, okay. And then when you point that out to physicists, they say, no, but the matter is just the space that expanded that way, as if, you know, the matter in the space wasn't following, right? Like, anyway. So, I'm not gonna start ranting. It could be a very long day if we did. So Cyprien is showing Yeah, go ahead.
Yeah, so here is a way of modeling, for example, the atom, I mean, the combination of a proton and an electron. And if we remove the source here by putting a zero, we obtain a solution that effectively converges to zero, meaning that the electron should fall onto the proton in the nucleus.
Yeah, so it's completely inconsistent.
Inconsistent with what is observed.
Yeah.
Oh yes, we need to introduce maybe creation annihilation.
Yeah.
Maybe we skip this.
Right.
So Dirac, when trying to solve this equation, came up with two different type of operators. One operator was the creation operator, meaning that from the vacuum fluctuation, like Olivier said earlier, it is possible to create a pair of particle and antiparticle. And this creation operators at a certain frequency is able to create a quanta of energy, which is h bar omega.
Like a photon.
Like photon. And on the other side, we have the annihilation operator, which if we combine particle with an antiparticle, we can annihilate the pair of particle and antiparticle. Then it goes back to the vacuum, to the quantum vacuum.
While emitting,
Yeah.
a photon. Yeah. Okay. So in the gamma ray range.
Yes.
Right? So this is the way vacuum fluctuation, this 0 point was basically described as like, Dirac called it a sea of energy popping in and out of existence. And it was called virtual particles just because it happened so fast that in general, people thought they could just call it virtual and ignore it.
Yeah, because it's so far that we cannot observe them, but we can observe the effect of this creation and annihilation process.
Correct.
In the experiments.
In the experiments, yeah.
And the way we are talking about the creation annihilation operators, because one of the main results of quantum mechanics is the non-commutativity of the operators, meaning that if we create and annihilate a photon, it's not the same as annihilate then create a photon. It's that there are some remaining energy that is represented here by the one. And contrary to the first case where we have the zero as a source term, here if we add the source term coming from the 0 point energy,
0 point energy.
then we can have a solution of this equation where the electron remain at its position and keeps rotating around the nucleus.
Yeah. Instead of inventing a quantum number and just saying that the electron is stuck in an orbit because of its quantum number, which
is no more an orbit.
Which is
for
what?
them. For them now it's not.
It's no more in orbit. It becomes a cloud of probabilities of the proton being there or not there. Yeah.
Extended all over the universe.
Yeah, well, so then again, quantum mechanics go esoteric, outside of the physical, nature of reality, and like we're just writing math and, don't try to visualize it. It's not an orbiting thing, right?
Yeah, right.
However, when you put the 0 point energy source, at least the oscillator has a chance to exist, right? Otherwise, it would dampen. It's just like, okay, let's go back to the spring and the ball. Like if you do this with the spring and the ball, it's gonna continue to oscillate. But if you stop, right, it's gonna go again for a little while, but then it will stop. It has to do with the conservation of movement and angular momentum.
Yeah, because there is friction.
Yeah, because there is entropy. And so this is like really inconsistent, and we could go deeper, and in the paper we go deeper, we show that actually, that removing it makes quantum physics commutative instead of non-commutative, and it breaks all of quantum physics. So you shouldn't and you can't really remove it, right?
Yeah, exactly, yeah.
So
And Another point that we wanted to stress here is that generally quantum vacuum fluctuation are deduced from the Heisenberg uncertainty.
Yeah, so this is a fallacy, I would say, okay, that is coming from the educational system not really doing the correct job, where, you know, physicists are told that zero point energy is the result of Heisenberg uncertainty principle.
Maybe we can remember what principle is
Right.
in physics.
So go ahead.
Yeah, a principle that it's an hypothesis that we are making to make the theory work. It means that we can't prove it,
Right.
but if we make it as an hypothesis, we can make the theory work, the rest of the theory work.
Right. So Heisenberg uncertainty has to do with a certain amount of uncertainty in our equations about the position and the momentum of a particle, or the relationship between the two, and
And it's linked to h bar, the quanta of action.
the quanta of action of the oscillator, and basically, you know, the way it's taught today is that this uncertainty produced this residual energy we call zero point energy, which is completely false, right? Zero point energy is a result of Max Planck exploration of a black body radiation, you know, thermodynamics that is like completely proven and demonstrated and all this, and it's very solid and all this. And the result, so now imagine you have a particle that's constantly being bounced around by the field, the zero point energy field. Well, it's going to produce an uncertainty. So there is about its position and where it's going. And so uncertainty principle is a consequence of zero point energy, not the, you know, zero point energy is a physical thing. The uncertainty is a problem with our equations, and that's being reversed, like completely reversed. And so that's a big problem, because if you read on, you know, the internet and so on, actually Wikipedia does a good job on zero point energy. They don't make that error. But, you know, everywhere else you'll see zero point energy is a consequence of Heisenberg uncertainty, and it's exactly the contrary. Okay, so one way, and we're gonna stop really soon. I know you guys have burning questions, and we're gonna go a little longer because we lost some time. But, you know, one way that you can calculate the energy in a region of space of a bunch of electromagnetic fields that are bouncing around, a bunch of waves that are found bouncing around, is what we call correlation functions, a set of equations. And it describes, so it's the equation that we have on right now. So it looks complex, but it actually is pretty simple, right? Like the equal sign, on the left of the equal sign is the result of what's on the right, and on the right is like one part that describe a wave you see in green there, a wave that's going to the right, and you know the other part after the plus is describing a wave that's going to the left, right? So it's two waves colliding, right? You can think of it. It's going to tell you how much the waves are canceling when they interact, and at a certain scale. So like at a certain, you know, scale of interaction. And that's the tau that Cyprien is showing. And so we calculated this, okay? We calculated, so on the right we're showing if the phase between the waves that are colliding was exactly 180 from each other, they would fully cancel out, right? 180 degree, you know, as we're showing on the right there on the top, you know, they would totally cancel out. And if they were perfectly in phase. You see the red represents the energy. Then the red is actually not right there. It would go to infinity, but since we can't make an infinite wave, we stopped it, somewhat, shorter than infinity. So you can see that, and the tau, which is the time, is describing the phase. So we calculated if the phase between the two waves was the length of a Planck entity, of a Planck length, which is like the smallest oscillation of the electromagnetic field, what would it give? The energy, like the red, constructive wave that would come out of it, what would be its energy? What would it give? And we got the Planck density. We got the density of the quantum vacuum, the 0-point energy, if you stop calculating, not to infinity, but if you stop calculating at the Planck length, at the smallest grain, right? And so that was remarkable. We got the right answer right away. And then we said, okay, well, what if the phase is the phase of a proton? So you can go to the next one. That is the tau, the length at which the phases are interacting, the waves are interacting, the phase between the two was the length of the characteristic time of a proton, like the time it takes a proton to go around once, right? And we got, this is in joules per meter square, we got the exact value of the mass of the proton. This is given in energy because that's typical in physics, but we got the mass of the proton. This is in the first part of the paper, and it's absolutely solid. It's analytical from the beginning to the end. We've received letters from very prominent physicists, certifying that it is consistent. And so why is it so important? Because we just proved that the energy that makes the concept of mass, that makes energy, is actually coming out of this fundamental field of energy at the base of reality, something that was called ether before by Maxwell, James Clerk Maxwell. Before that was called all kinds of names in ancient civilization, that there was a fundamental field of energy and so on. And so that's really powerful. It's really powerful that we can prove analytically. That's where mass comes from. You don't have to invent a Higgs field, an Higgs mechanism. You don't have to do all these things, and you get the correct value for the mass of the proton, 100%. It's remarkable that it gives the exact value. Now, if you, and actually one of the letters we receive is from a foremost expert in the field of 0-point energy, somebody that worked in some of the largest institutions on earth in physics. And so, and he thought it was a remarkable result. Then there is, then we continued by saying, well, now we have a little cavity. We'll check. We already showed this. We get 100% the mass. We don't get 5% like the Higgs mechanism. We get the whole thing. And then when 0-point energy was discovered by Max Planck in much later in 1947, a guy called Casimir said, hey, if this field really exists, if I put two plates close enough together, I can eliminate some of the energy that's in between the plate enough that the outside would have the energy and would push them together, create a pressure or a force. So it's called a Casimir effect. It couldn't be verified till the 90s, 97. until we could get two plates that close together, because they have to be microns apart, because remember the field is occurring at the scale that's so much smaller than us. But they got the effect, so we're actually producing a force. And it's funny, I think it was an AI, it was an AI generated website called Perplexity, I think it is. Perplexity, and it was remarkable because the AI was insisting that you cannot extract energy from this field, and then obviously the AI was a little embarrassed because at one point he had to address Casimir force, and the answer he gave was, well, Casimir force is so slight, right, that we can ignore it because it's extracting energy from the vacuum energy, like it's producing a force. And that would be saying, the Model A, the Ford Model A, was such a slight, ridiculous machine because it broke all the time, and it couldn't go very fast and all that it could just be ignored, right? Like proof of principle. Clearly, if you're able to extract a little bit of energy, even if it's very little, you're extracting energy, and you can no longer say that it's impossible to extract energy from the vacuum. And because after that, they did the dynamic Casimir effect where they pump the plates and then photons come flying out. There's all kinds of evidence that the zero-point energy is involved at the quantum scale in the atom and all this. So to say that and our equation just showed that the mass or the energy of matter is coming out of that field. So nature is definitely extracting it. And the reason why they're saying that is because they put it to zero. They say it all cancels out, so you can't get anything out of it. And they haven't realized, the world has not realized, that the matter they're looking at is actually when it doesn't all cancel out, and the residual energy is what we call mass, and it's remarkable. It's just remarkable. And so okay, I'm gonna stop ranting. Okay, so that was the last slide on that section. So then we followed with the Casimir effect because we have a little cavity. And so we are eliminating some of the waveforms that the longer waveform cannot get inside the cavity of the proton. So we thought, okay, well, let's calculate the Casimir force of how much force they would be applied on that proton from the zero-point energy. And then we got this value that just happened to have recently been measured, which is the internal pressure of a proton, right? Which is thumbs up to those guys that measured that. That's like incredible that we can measure. It's not like you can grab a proton and stick a meter in it to check out how much pressure is in there. It's a really tough thing to do, and they did it, and it's been actually just confirmed a second time now. And so this value we got it's called the color force. It's the force it's the nuclear binding force that holds the nuclei of the atom together. So we actually got the right force, like the color force or the strong force that we had to, in standard model, they had to fudge it in because they didn't know what was holding the protons together against their electrostatic repulsion. And, we got the right value just like that. So we got the right mass and the right force. And in the rest of the paper, you'll see we get, all the other forces all the way to gravity right out of it. And so we're showing there's only one force and there's only one energy. And that's that fundamental field, and everything emerged from it. And it ain't virtual. It's actually very, very real and solid. And so I want to... Okay, so we're going to stop there because otherwise we're not going to take questions, and that would really be a bummer. But we have so much more to show you about the paper. We're gonna do another one very soon. Please stay with us. Like, this is really fundamental, because you might think, why do I care about all this? Like, well, because we just told you that your existence, which is made out of protons and electrons, and we can show that the electron is the same case for 0-point energy, is actually emerging from a fundamental field that you're part of. And this is critical to know in your existence, like even just as a concept philosophically, but imagine the critical part of this being like, all of a sudden you understand there is a direct path of engineering to actually, because there's a way to create a little gradient difference in the structure of the vacuum that's better than two plates. Like, two plates is like, I'm kind of surprised it even worked, right?
But actually, nature with the gecko is reproducing it. The
Yeah.
gecko are the small like reptiles. Maybe you can talk about it. When the reptiles that can climb on the walls
And windows.
Yeah, they were measuring the force, the Casimir force,
Right.
produced by the little peeling. That's what the hairs are called on the gecko's feet. So the geckos have these padded feet. And if you've seen them, they have a really high folded structure, a lot of surface area.
Yeah, at the microscopic level.
At the microscopic level, that surface area
Same
is
as for the Casimir plates. Same distance.
same distance, and so they're covered with these hairs that generate a Casimir attractive force, so that a gecko can adhere essentially to any surface, because the quantum vacuum
Is sticking them.
having its stick to glass.
That's awesome. I used to have a gecko pet when I lived in Hawaii, and he was awesome. He would run after my mouse on my screen all the time, and so yeah, I mean that's remarkable.
And understanding that, they were able to build technology upon it. Polymers, but very particular polymers.
Because it's pretty remarkable that it can use the Casimir force to adhere to the surface and then also unadhere.
Changing the geometry.
So you're talking about how you can modulate the Casimir force with geometry.
Right.
It's applicable technologically.
Yeah, and actually just last week a paper came out showing that they were able to modulate the Casimir force between two balls, right? And get it to go from attractive to repulsive, depending on the geometry of the balls, right?
Yeah, even modulating the Casimir force with magnetic fields.
Oh, right.
As well.
Yeah, with the magnetic field. Yeah, that's right.
Magnetic field.
Yeah. So, I mean, this is no longer, 30 years ago when I was talking about this, it was basically voodoo. Everybody ignored me. Everybody looked at me like whatever, and, now there's so many, it's emerging, and it's emerging fast. And yes, fundamentally in your awareness, to be aware that you're in contact with the fundamental field that makes up your existence is critical. But as well, in your society, when you have a society that's extracting energy directly from that fundamental field, which is extremely dense in energy, right? I mean, as you saw, it goes to infinity if it's not renormalized, but even when renormalized, it's 10 to the 93 grams per centimeter cube. It's more than all the energy of all the stars in the universe in a centimeter cube of energy, of space. If you can extract with very little amount of that energy, you're running your whole world for thousands and thousands of years with like less than a centimeter cube of space. So I mean, like it's vastly transformative to a society, but you have to understand the physics of it. You have to understand how to utilize it, and that's what we're doing. Never mind the application to health and consciousness and all this. I mean, this goes far when you realize, like, when you understand the foundation of physics, actually, the foundation of what physical object emerged from, right? So maybe we can start taking questions.
Yeah,
Oh.
we have question on technologies, we have question on astrophysics, on black holes,
Okay.
which
I think there was one previously that found an error in one of our annex. There was a
C
C.
square missing.
It is a C square missing. Yeah, so that was a typo. We'll repair it. Thank you for pointing it out. And it's encouraging for us to see that people are reading the annexes as well as the paper.
Yeah, it depends on whether we express the density in mass or in energy, as we saw earlier.
Yeah, and so we were
It's square, yeah.
we were doing in energy, and we forgot to
Yeah.
put the C.
The C square.
The C square. So, but like, we'll repair it. No worries. Thank you so much. We appreciate. Thank you. Clearly, some people are going through the equations.
Yeah.
And how many downloads are we at?
49.
49. Woo, we're approaching the 50,000 downloads. That's a lot for a physics paper. That is a lot for physics. And, so far, nobody has pointed fundamental error, mathematical errors. There is none.
On this topic, we have a question about the peer review process.
Okay.
And how far we are in this process.
Okay.
So as you said before, we received like positive feedback from researchers, experts in their fields.
The expert in their field, in the specific field, and we are in the middle of the peer review process. Those things take a long time. We're going for very high level journals. The paper is long. It's not easy. Of course, objections conceptually, because there's no mathematical errors or because it's analytical throughout. And we're not inventing anything.
One funny objection we get from one reviewer is that we couldn't mix quantum mechanics with general relativity because it was forbidden.
Right, it's forbidden. Well, sorry, we solved it. We did mix it, and it's mixable since the universe is one thing, from quantum mechanics to general relativity, right? The small things make up the big things. So, just so we know, for that reviewer over there, listen, guy, check out the equations instead of making an opinion before actually reading the paper.
Yeah, philosophical opinion.
We're not interested in philosophical opinion. We're interested in, good, criticism of our formalism and any errors that we may have done, because the whole thing is analytical. We didn't invent dark photon, we didn't invent anything. We actually took what's pretty well already there and we rearranged it. We put the things in the right thing, and it gave the right answer all the way to gravity, right? Yeah. So okay.
So
we're in the process.
do you want
Be patient with us. We're doing the best we can. It's not obvious. The peer review process.
usually 6 to 12 months, depending on the journal we are applying.
Right. And the idea that peer review is completely clear and fair, and that it's if something is true, it should be easy to go through peer review. That is just not the case, and it's been shown in many different studies that are peer reviewed.
Starting with Einstein paper on general relativity.
Yeah, exactly. Yeah. You want to talk about it?
No, let's speak like question.
Okay.
Because
So it's in the process.
Yeah.
We have faith that the physics community will come around.
And we think it's a very important process because we are developing this theory not for us, not only for us. We are developing it for us because we need it to develop the technology. But the fact that we are sharing it with the scientific community is it's because we want the scientific community to work on it.
Right.
So we want their opinion. So
Right.
it's not that we are doing the reviewing process as a formality.
Right.
We want to interact with the scientific community, have feedbacks,
Right.
and build on every constructive criticism they could give us.
Yeah, of course. Yeah.
So, which topic will you want to start with?
Oh,
Black
yeah.
holes, astrophysics, technology?
Sure, black holes,
Black holes.
astrophysics, or even biology, to have Ines and William.
If you want to, there are questions about the black hole and how we could demonstrate that the sun is a black hole. Because William, you wrote
You wrote that article
very appealing article on this topic.
with a little bit of my help.
Oh, we did it together. Yeah. That was one of the exciting things about this development on mainstream scientists, so scientists from Berkeley, Yale, re-examining the question, could there be a black hole, a primordial black hole at the center of the sun? So this was a question that was originally posed by Stephen Hawking. And really what he was seeing, and this is back in like 1974, he was looking at, okay, here's the energy density of the early universe based on the inflationary model. But at this energy density, black holes will form directly from the energy available in free space. These are called primordial black holes. And in fact, if you run the calculations, there should be a lot of these primordial black holes of varying sizes. So like, it almost would be like every proton would be a black hole. That's about the number and distribution you would expect to see.
Yeah, that's actually the statement they give, no?
Yeah. And he was looking at proton-sized black holes, primordial
Right.
black holes.
Primordial.
And Stephen Hawking said there's some interesting things in this paper. I mean, he said that they would form stable atoms,
Right.
and we should be able to see these black hole atoms in cloud chambers.
Yeah.
And he said we should expect to see them at the center of stars. So if you have a large gravitating body like a star, objects are going to be attracted to it. So if you have a bunch of primordial black holes, not only are they probably going to form with the star, but they're going to eventually make their way into the core of the star.
Yeah, a little more push thought on that would be that the black hole made the star, like in the first place, that the primordial black holes were not just made in the scale of the protons, but that there was larger ones that were made that became the core of stars, or the core of galaxies for sure, and then the core of stars.
And this, what Nassim just said, this is being observed right now. I mean, when you look back with the James Webb Space Telescope at the earliest epochs of the universe, you see these supermassive black holes, and some of them are like a 1-to-1 ratio with the stars around them. Right? So the galaxy is a black hole. And what happens over time is that the galaxy is built up from the black hole. The black hole builds the galaxy around it.
Yeah, so all of a sudden the concept that a black hole just sucks up everything around it is false. I mean, we know it's false, but it's being propagated through the popular science since so long that they're repeating that story that black hole just sucks up everything. If black hole sucks up, I predicted there would be a black hole in the middle of all galaxies, right? There was other people at the time that were predicting that, but they were basically the fringe, but then, at the time they were saying, the people that didn't believe that, which was the majority of the astrophysicists, they were saying if there was a black hole in the middle of all galaxies, there would be no galaxies because they would be all sucked up in their black hole.
You know what? Some of the feedback we've seen, they're saying the same thing for the star.
The exact same argument. And every time I told them, no. This thing is spinning near the speed of light, which now we are able to measure. We're measuring, I think, 90% the speed of light. We see the material around the black hole in the middle of the galaxy spinning at 90% the speed of light. It's very doubtful because they were trying to tell me that no, the black hole can be stationary. It's very doubtful that it's not because the Schwarzschild solution is a stationary solution that the universe is making stationary black holes. The reason why the Schwarzschild solution is a stationary solution is because when Carl Schwarzschild was dying, which he died 2 weeks after solving Einstein's equation, he just approximated the most simple, solution he could do. And so he removed rotation and charge from the thing so he could, that doesn't mean that there's actually things out there that don't spin. Okay. So anyway, yeah. So of course, if something is spinning at that speed, what happens?
You've got the centrifugal force.
Yeah.
That is counterbalancing.
Coriolis force.
Gravitational attraction.
Gyroscopic effects, and those are huge.
Yeah.
So actually, very little can fall into a black hole. Very little. It's got to have the right incidence on the pole to get sucked in.
If you look at the centrifugal force and the radiative pressure, because when the plasma is forming, let's say it's infalling plasma around the black hole, it's spinning, it's accreting, that plasma heats up and starts to emit energy.
Right.
So you've got a radiative thermal
Pressure.
of pressure and centrifugal force. The plasma can lock into place essentially. It's extremely stable.
There's all kinds of stable orbit around black holes.
Yeah.
There's even equation that shows that there's stable orbits inside black holes, inside the event horizon. So,
Next question on same topic.
just to finish on the black hole sun, that means that when we see a star explode and go supernova, and afterwards we go, oh wow, it made a black hole. It's the other way around. They have the story exactly reversed. There is a black hole. It makes a star. It goes through an evolution. It makes a star because it's accreting material that's staying in orbit around it, right?
It's also creating matter.
And but we won't push it to that point. It's too much for most people already. And then it goes through the carbon cycle. All the material, the plasma that's accumulating, we see the carbon cycle on the sun. It gets more and more dense in the orgosphere, in the plasma, and eventually it makes shell, and the shell builds up in pressure, and the thing explodes. And when it explodes, what do you see left? You see the black hole that was in the center. It's the other way around. And then the material that was blown out gets caught in smaller ones, and it makes planets. And that's why we're seeing planets around almost every star that we observe. We thought planets were rare. In the beginning, 30 years ago, people were telling me, no, planets are super rare in the universe. I'm like, what is your data to prove that to me? Because my theory says they should be very, very prominent. Every star almost should have, if they gone through at least one cycle of supernova, should be, have stars around it. And that's exactly the first planets around. The first planets, exoplanets that were found around pulsars in the most harsh, literally right after a supernova explosion, and that's not been resolved. But anyway,
Was the question how we might be able to detect a black hole?
Yeah, which kind of measurement? And it's interesting because you answer in the paper that a very strong evidence that the sun is a black hole is the neutrino anomalies.
Yeah. Well, because it's been suggested that there might be a way to directly detect the black hole at the core of the sun via helioseismology. So seismological spectrum analysis, essentially. Now, when there's this thing called the neutrino problem,
right,
which was that the normal standard model for the sun said that there should be X amount of neutrinos coming from the sun. When they measured it, it was 1/3 the value. This was a problem because like the
It's
great
the fusion model of the sun.
fusion model of the sun. Now, so when that happened in the 1990s, they did seismological studies of the sun, and they said, oh no, there's no structure in the center, because people in the 90s, when that happened, were looking at, is there a black hole in the sun, like Stephen Hawking said? So they do those studies, and they say there's no black hole in the center. One of the things, though, is that those studies they were doing, the helioseismology, was for a 2D surface. So they were looking, modeling the oscillations, actually like mechanical oscillations, acoustic oscillations on the surface of the sun.
On the surface of the sun.
Not in the center.
Not very deep into the center.
Yeah.
And actually, some of the maps they were producing, I remember them, had in the middle a white spot with an interrogation point and a question mark in the middle, because they didn't know what's in the middle, because helioseismology is not going to tell you that. But there's one thing is for sure, the sun cannot be a complete solid sphere, because it rings like a bell. And that's inconsistent with the sphere that's full. It's like, it would be like a bell that's full. It wouldn't ring, It wouldn't ring very well. So, if you have a black hole, which has, absorbed some of the material around it, and then some material is in orbit around it, and then it radiates because there's a lot of heat, because that thing is spinning and producing a lot of energy, then the total mass of the sun would be what we assume from our measurements, right? But it wouldn't, planets would all be at the same place, everything would be all at the same place. We just wouldn't have any clue that there's a small black hole in the middle of the sun. Either than sunspot. Sunspots is kind of a big clue. So I tried to bring that up in the 90s, but when I was bringing that up in the 90s, they didn't know what sunspots were, so they said it was a surface event, and it was an optical illusion from, the photons getting, because of the magnetic field, getting sucked up by the magnetic field. Now we've discovered, as I told them, that actually, sunspots, which are sometimes 14 times the size of the Earth, are huge vortices on the surface of the sun, where you see the material falling into the middle of the sun. And what comes out? X-rays. They're X-ray emitters. The largest X-ray emitters on the sun are coming from sunspots. And that's exactly what happens when material falls into black holes. It eventually emits, X-ray and gamma ray. So, there's a lot of evidence, there's a lot of clues, but it hasn't been understood very well yet. It's gonna get there, it will be like the prediction of the center of the galaxy. It will get there. We just gotta be patient. We're gonna help it along, hopefully.
So there was another question on black holes.
Yeah.
About what is the semi-permeable structure of the event horizon of the black hole, and how is it linked with the black hole emitting information?
Right. I wish we had time to get to that second part of the paper, because we addressed Hawking radiation.
Yeah.
But yes, I mean, it's just like the semi-permeable boundary of the mitochondria.
Very, very interesting. But it's almost like you're describing the same setup.
So yeah, exactly. So you can imagine, first of all, think of a black hole. Okay, so based on the solution of the mass we just give, think of the black hole as just the vortex of the Planck plasma, of the 0-point energy in that region of space. When the vortex is spinning at near the speed of light, it produces a boundary condition, a shearing, at the horizon. And that horizon, I wish I could give you the details on that. So I'm going to say it, and I'm going to say to you, if you extrapolate from what's in the paper, you'll see what I mean. The shearing that's happening at the speed of light at the horizon happens to be equivalent to the Schwarzschild solution, to Einstein, the energy of a black hole. And so basically, we found the solution. We just don't know that it's the vacuum, it's the quantum vacuum oscillating, spinning inside that's making the black hole. We think that a black hole is the result of mass accumulating in a region of space till not even light can escape it. But actually, the black hole is there prior, the black hole makes the mass. It is mass. It's a dynamic of vacuum fluctuations. And so, again, that's reverse. And so,
actually, any mass is a black hole.
yeah, exactly. And if we had time to go through the rest of the paper, you would see that. But we will next time. But basically, think of it. So you have an object that's spinning, and space-time or quantum vacuum fluctuation shear at the horizon, and it produces a lot of energy. Some of the energy is radiated, some is absorbed by the black hole, and that's what we call Hawking radiation. That's something that Hawking came up with, showing that black holes can emit thermodynamically. And we show that the thermodynamic emission of a proton black hole is equal to its mass, that the energy that we measure for the black hole, that we just showed you from the correlation function, is so remember the little virtual particle, one comes out, one comes in. Think of that across the event horizon of the black holes. We call it semi-permeable because there's particles emitting and the particle falling in, and that produces real particles. This is how Hawking described Hawking radiation. And we link that to the vacuum fluctuation that makes up the black hole in the case of a proton or a star or a galaxy and so on. So, I don't know if that clarifies it for you, but think of an exchange of information. Remember, you can think of this stuff as information. There's an equivalence in physics between information and energy. So you can think of it, information is going in and information is going out. And that's how the universe informs itself.
And actually, it's very interesting and important, this point, that information is exchanged, because when we are looking only at Hawking radiation, they think that there is no information exchange. But
right.
now, with even a recent paper published in Nature, we know that electromagnetic emission from an object is carrying information about this object.
Exactly, which is continuous equations or that were solved just recently. It's remarkable that showing continuity equation that are showing that any electromagnetic field that's bouncing around all the objects here on the table
is carrying information about
the object, its position, if it's moving or not moving, what's going on, and that information can be actually decoded.
Yeah.
Yeah, and those are really important equations. Remarkable, they solved this.
It was an experimental paper, so they did measurement.
And they got the right answer. Yeah, it's remarkable.
Do you want
in the context of zero-point energy, which is electromagnetic fluctuation, it's telling you that the field is actually informed about the position, about everything that's in the universe, that's in it. Like it has really deep implications.
And it gives you the mechanism for the space memory network.
Yeah.
Meaning like how the information is transported across space and is encoded in space-time.
Exactly. And then the network of the vacuum field, it's remarkable because it's like something that William and I wrote. When we wrote that?
2015, I think it was published 2016.
Okay, yeah. And it made some noise. It was cited by very good researchers in Europe and so on. And, now we're going to be able to write this exact, neural network of the universe much more precisely. And it's going to be such a powerful paper. It's going to kick ass. And it will show the relationship between the natural flow of information across the network, right, from the universal size to the atomic size, and eventually to the organization of biology, and eventually to the complexity of biology, and then eventually to the event of consciousness, like meaning the system running enough feedback of information that it's becoming self-aware.
And that's another reason why this paper, The Origin of Mass and Nature of Gravity, is so relevant, so significant to everybody, because that's the basis of how you're going to be able to describe a memory property of space, information flux through space. That is the process by which the self-organizing systems emerge into the living system. So, it's directly applicable to your relationship to this information field.
Yeah. Okay, more questions?
Yeah, on in astrophysics, maybe. One is about, does the universe have an event horizon?
You want to answer that one? You've not said anything.
Yeah. So in the paper we demonstrate, we show it a little bit earlier in the presentation, that a way that we solve the problem of dark energy and dark matter in the standard model was to consider the universe as a black hole.
Mm-hmm.
And once we calculate the energy density of a black hole thanks to the holographic mass solution, we found the exact measured value for the density of the universe.
Right.
Without requiring any other matter, any dark matter, dark energy, and
Right. Because we're showing that the vacuum fluctuation is the source of the mass.
the source of the mass.
And so you can't ignore quantum vacuum fluctuations.
Exactly, yeah.
Yeah.
So
And actually, the cosmological constant that they need to add in their Einstein field equation to make it work comes naturally from
From our equation.
Yeah.
the screening mechanism from the Planck
Yeah.
plasma.
Yeah. That's remarkable, but we haven't published that yet.
Oh.
So this result suggests that our universe must have actually an event horizon, and
Yeah, we live inside a black hole.
we live inside the black hole, so it's not so terrible to be in the black hole.
No, we're doing good.
Yeah.
It's not so stressful. It's got lots of air,
And yes, and sometimes we picture ourselves a black hole as something very extremely dense, but this has to be compared to also the size of the black hole. For example, if we create a black hole of the density of the air, atmospheric air that we have here, if we create a black hole that is large enough to reach, for example, from the center of the sun to Mars a little bit further, then we can create a black hole. So
a bubble, the size of the orbit of Mars,
the orbit of Mars,
maybe a little bigger.
a little bit bigger.
Yeah.
With the density
Of the air.
that we have here.
Yeah, so you would have the density of the air.
Exactly.
It would obey the condition of a black
Exactly.
hole.
So if we consider a black hole with the size of the universe,
Yeah, can be really low density.
yeah, it can be very low density.
Yeah.
And
And it
actually,
happens to be the density we measure.
when they measure the density of the black hole at the center of the galaxy, they measure the density very close to water. And actually, they measure water.
Yeah.
The black hole at the center. Of
So the black hole at the center of a galaxy is big enough that the density of supermassive black holes is about the density of water, and so on. And so it really kind of makes sense. Right? And then on top of it, when you calculate the density of a black hole to the size of the observable universe, you get the value of
critical density.
the critical density of the universe, meaning you get baryonic mass, dark matter and dark energy. You get, like, when you put them all together, that so you can tell that it's like correct, right?
What about the surface area of all protons in relationship to the surface area of the event horizon?
Yeah, that's kind of cool, but that will be in the next, thing, because that's at the end of the paper. We haven't addressed that. Okay.
There is like a good question about more physics in general. Someone is asking, it would be nice to have a list of all the assumptions that were made that caused the physics community to go in the
Array. That's a good thought. That would be nice.
It's coming in the book.
Yeah. Oh yeah, it's in the book.
That's gonna come.
She just revealed we're working on a book, right? So that's good. It will be in the book. That will be nice. It'd be a nice table.
Yes.
Oh, I have some ideas for that. That's a great suggestion. Thank you. But Ines already had thought about it. Seems like, yeah. Yeah.
Yeah. Olivier also, yeah.
Okay, good. Yeah, so it's coming up. It'll be in the book. Yeah.
Yeah, that's coming.
Do you want to talk a little bit about technology? There are like many questions about technology, and in particular, there is a good one. Do you already know what will be the eventual side effect of extracting zero-point energy at a huge scale on human health or for the universe equilibrium?
On universe health.
On human health.
Oh,
Sorry, English.
on human health.
Yeah, and more generally, if it will disturb
The universe.
the universe
Yeah.
equilibrium.
So like I said, first of all, like the energy density in a centimeter cube of space of the vacuum energy is more, if we just took everything that's in a centimeter cube of space, it would be more than we would ever need for billions of years in terms of energy in 1 centimeter cube of space, because it's 1093 grams per centimeter cube. That's more than all the energy of the universe by 39 orders of magnitude. Okay, so it's a lot of energy.
I think the question is more about is it the same kind of energy as nuclear power with all the side effects that you can?
Yeah, no, that's the thing. It isn't, because basically we're biomimicking, although not bio, we're physically mimicking, but we are doing exactly what the universe is doing, meaning all protons, all electrons, and all this is vacuum dynamics. We're just making a thing that's doing the vacuum dynamics as the universe does. So yeah, we extract energy from vacuum energy. However, when we use that energy, right, we're going to power a house or car, we are putting it back into the vacuum, just like an atom is doing, or your body is doing by thermodynamic emission, or atom, or so on. And so it really is like just a cycle. It's like putting a turbine in a river that's flowing, right? You're not, destroying the flow of the water. You're just extracting some mechanical power of the flowing water. It produced some destruction because you got to build a dam, you got to flood a region and all this. But let's say you're just putting a little turbine in the river down the road from you. You're not disturbing anything. So imagine basically these devices are basically just doing the same thing. They're like, as the flow of space-time, of this fluid dynamics of space-time is flowing, we're extracting, we're making a little energy out of it, and then we're feeding it back to it, because we're gonna burn it in thermodynamics and all that.
And more than that, actually, it's better for the near environment, because we are creating a current field.
Yeah.
And it's completely different from the current technology where we are like using explosion,
Right.
heating the system. Like nuclear power is just about heating something.
Yeah.
So creating a very large disturbance.
Right.
In space-time.
In space-time, yeah.
And with our approach, it's totally different, because we are creating like a current field.
A coherent
A
field.
current field.
Yeah.
To be able to extract this flow.
Yeah, good point. And when you create a coherent field, if this is the nature of how the mitochondria is extracting energy for the ATP of the body, which is what actually breaks down. It produces less and less energy and makes the cell have errors in copying, and that's what we call getting old. Well, if we can make a coherent field of vacuum energy, right, we can actually, create like this possibility that we can keep the mitochondria, what William was talking about, in a way that maybe it doesn't break down.
Because you can make a really strong case that one of the primary roots of aging is mitochondrial dysfunction. So this technology is potentially highly beneficial to the biological system because if you can increase the coherency, the efficiency of the ATP, keep it functioning in an optimized fashion, you can prevent aging. You can prolong lifespan. You can prevent that breakdown that occurs once you start to get mitochondrial dysfunction. So in that way, it's unlike any previous energy technology we have in that when you're working with a structured, coherent field of space-time, you can potentially have a highly beneficial technology in terms of its effects on the biological system.
Right. One more question?
One more question about, there was like a very good remark in the chat about this kind of technologies that have the effect of cooling the environment. And in fact, it's cooling the environment because it's structuring all the environment.
Mm-hmm.
So
this kind of technology.
Yeah, less Brownian motion.
Yeah. Cooler environment. Yeah. Instead of heating up, this is what inventors call the cold energy, cold power, cold electricity. Yeah. They've noticed that when they get these devices, commonly precariously being able to extract a little energy, which, can, run away in their devices a little bit, that they get like serious cooling effects. Where even the wires can freeze up and so on, and which makes it possible to actually, now I'm kind of opening a can of worms, but I'm gonna open it because it's things that I've experienced directly. So, just take it as my own experience. If you don't believe it, that's fine. But which makes it to be able to move like serious amount of kilowatts of power through like hair thin wires because they don't melt down. They actually cool off and become more and more superconductive as they cool off. And so you can get like a completely different thermodynamic experience from the energy device. Like it's a completely reverse paradigm of energy.
Both are producing and transporting the energy.
Yeah, exactly. Producing and transporting. All right. Well, all this has been super fun. I hope you guys are having fun on the other side. I hope we didn't bore you with too many technical details. And,
We have the same people as the beginning, or nearly.
Oh, good.
Even more.
Okay, good. I hope so. Then they're not too bored, or they might all be asleep and they didn't turn their thing off. But yeah, hopefully not. We are a small team. I just want to finish we really appreciate your participation, your help, everything you can do, anything you can do to help us. You can buy bonds, you can buy, art crystal, you can become a member, you can do all kinds of things. We're funded independently, and I assure you, all this stuff behind you, you see, it costs significant, money, and we have, we're doing what I believe is some of the most important work. And there's other labs doing really important work too. And like, please support us, help us, get us going, get us out there. We need significant amount of help. It shouldn't be 5 people here. There should be 10 engineers back there, and I don't have them right now. And so like, it's really critical that you help us, and whichever way, which is in some cases just being like participating in this Q&As, coming on, asking questions, collaborating, whatever you can do. We appreciate it. We love you guys, and we're doing this for all of us and for generations to come. And it's super critical at this time in history. So thank you for being there, and thank you for your time tonight. I can't wait to be with you guys again. All right. Thank you guys, and see you soon. Until next time, may the vacuum be with you.